Welcome back to ECE 320A. Homework number 10. Don't tell anyone, but that's due on Thursday. You can know that. I'm doing that to give you more time. We really haven't talked about the second part of that assignment, and that's what I want to cover today. Here are some office hours that are scheduled between now and your final exam. If you have already filled out your online teacher course evaluations, thank you. If you haven't, please try to do that in the next day. Those close on Wednesday. You will not have any more opportunity to fill those out until, well, you won't. It'll be done after tomorrow. And I do not see those results until sometime in January if I'm lucky. So it's way after your grades are posted. So don't think that that's going to influence or impact your grade in any way. The review session for the final exam is scheduled for Thursday. A lot's happening on that reading day, but that's in the afternoon from 2 to 3:30. If you have any questions, burning questions that you really hope that I would address during that review session, you may email those to me and I can try to integrate some of those or all of those depending on how many questions I get and how I can consolidate those. If you have some questions that are really bothering you or you really want to try to get well understood before the final exam is on Tuesday and it's from 10:30 to 12:30 in this room. Hopefully that comes as no surprise to you, and I hope that date is correct. That's the 17th of December. The process for the final is consistent with what we've been doing all along. I'll allow you to have one more sheet of notes. Maybe you'll have some formulas for two-port circuits on that in terms of the Z parameters and how you might solve for those Z parameters or what the equations might be if you had an interconnected circuit that contained Z parameters, and we'll try to talk about those today in class. Hopefully, if the recording works, we will have notes and video of the review session if you are unable to attend on Thursday. And there already is online on the D2L website a practice final, and the format's a little different. It's multiple choice. So you might look at that just to get familiar with it. I'm not sure the format that will happen this semester, but that's what happened that semester. That was many years ago. The reason I'm posting that, usually I don't post finals, is I had someone, I think it was a plant, in the class. I handed it out and I said, "Are you in this class?" "Yeah." I started walking up the stairs and the student exited very fast. So that final is out there. I just decided to let everyone see it. I don't know how much he made off of that grab, but I started taking out after him, and then I said, "I have a classroom full of students with finals on their desks. I better not be doing that." But it's a good thing I didn't catch him, actually. Wouldn't have been pretty. All right. So what do we want to do today? We want to finish up the filter example that we had semi-finished last time. We derived the normalized third-order Butterworth filter. Let's just see how we could then translate that into a maybe more practical situation where we have a specific bandwidth, not just fixed to 1 radian per second. And then we'll discuss all of Chapter 18, well, parts of Chapter 18, enough to hopefully get you comfortable working the problems that you have on the homework number 10, and final exam questions that might be related to two-port circuits. Here is what we had last time, and you might just double check the structure of the second order section. For some reason, I was not sketching it very well. Actually, I was sketching it incorrectly. So make sure that it's sketched properly. I think I had, the resistors going into the inverting terminal. Make sure that it's consistent with the figure in the text, but this is now how you can build higher order filters. If you had a fifth order filter, you could simply put another second order section in front of this, and then you have a fifth order filter. Now, the parameter values might be different, and that's what determines, or those are determined by the tabular entries, or if you sketch the Butterworth pole pattern, those poles then impact where these normalized R's and C values will be, depending on the filter order. In this case, we needed our denominator for the second order section to have a polynomial, a second order denominator, since it's a second order section, to be s squared plus s plus 1. The b1, it's not maybe obvious, but it's right there, and it's sitting there as a value of 1. B sub 1 in that particular, when we have a third order Butterworth pole pattern, we want our three roots to solve that product of terms. And that will give us then one pole at -1 and two poles separated by what angle from the real pole. So we have 360 divided by 2 times the filter order. So it's 360 divided by 2 times 3, or 360 divided by 6, or 60 degrees. So the roots of this are going to be 60 degrees away from this pole at -1. And if you do the factoring, you'll get -1/2 plus and minus j, the square root of 3 over 2, I believe, for the roots of this quadratic, s squared plus s plus 1. That comes from the table, or it comes from your sketching. And then you know, since this particular spot was the location for B1, in our derivation of how to find the parameter values for a quadratic corresponding to that particular second order section realization, here we can see that B1 is actually 1. C1 was 2 over B1, so in this case it becomes 2, and C sub 2 is just the reciprocal of C sub 1. And the first order section, which gives us that pole at -1, our R's, R1 and R2, are both equal to 1, and our C value is equal to 1. And hopefully it's clear what parameters I'm defining by R, C1, C2, R1, R2, and C. Is that clear? Because now when we start to change the frequency or the bandwidth of this low-pass filter, right now this is a low-pass filter. How big is it? What's the order of that filter? It's not that hard, is it? It's a second order and a first order. It's third order. What's the bandwidth of this filter right now? If we realized this filter, what would be the low-pass frequency's bandwidth? What's the half power frequency, or what's the -3 dB frequency? 1 radian per second. What we typically want to do is something different from that, but this now represents a third order low pass Butterworth. Butterworth just defines those pole locations. You could use these same circuits and have different pole values by a different choice of R's and C's. We've picked those R's and C's to get us a Butterworth filter. And what's so significant about a Butterworth filter? Pardon? There's no ripple. We didn't really even speak of ripple, but there's no ripple in the pass band or in the stop band. But if there's no ripple, there's no bumps on our pancake, it's flat, isn't it? And it's flat as far or as close to the cutoff frequency as possible. That's maximally flat. That's how we define this Butterworth pole pattern characteristic. That's what the Butterworth gives us. It just gives us the pole locations. We've agreed that that particular third order realization, that circuit, had a bandwidth of 1 radian per second. What if we wanted a bandwidth of 200 hertz? What do we do now? Then what? Do you remember? I'm climbing a, no, I was scaling a mountain. So we need to scale. We need to scale something. If you're just listening to this, you have no idea what I'm talking about. I'm just doing all sorts of crazy things in class, so unfortunately you missed it, right? But we now need to frequency scale with this parameter k sub f. K sub f is the ratio of the new cutoff frequency compared or ratioed with the old frequency. That defines our frequency scaling parameter, which we had defined to be k sub f. In our case, we need omega nu not to be just 200. It needs to be in the same units as omega old, and omega old was in radians per second. To be consistent, then, we need to have omega nu to be 2 pi f, or 2 pi times 200. Omega old is just the 1, which says now if we need to frequency scale any of these parameters, the r's and the c's, that's the k sub f that we use. If we frequency scale the r's, how do they change? Trick question, wasn't it? They don't change. Our resistors are not dependent on frequency. If you looked at the impedance of a resistor, it doesn't have an omega floating around like the L and the C do, does it? So the resistors, if you're simply frequency scaling, you don't have to adjust the resistor values. Yes? Pardon? Yeah, I don't know how I dropped a pi. I don't normally miss a pi. Oh, but maybe this pi I might. But if it was a real apple fruit pie or something, I wouldn't have missed it. Yes, thank you. That should have been 400 pi. And it shouldn't be hertz, should it? Man, you got me thinking about pi, and look out. So this is now, I'm just making sure you're paying attention. Is that okay? Are we better now? And what am I doing? Gosh, you guys, k sub f is dimensionless. I just canceled all my units. My notes are correct. I just am getting so excited. I was scaling mountains and everything else up here. So now we have a frequency scaling factor, k sub f. It's just 400 pi, right? When we change capacitors and inductors, we better not change the units when we scale them. So that's a dimensionless parameter of a value of 400 pi. Well, this will now be a little bit boring if we don't have to convert the resistors. So let's just also make another assumption. Let's suppose that we also I'll let you in on a little secret. Somebody spilled coffee up here, and all I can smell now when I bend over is coffee. Man, didn't get enough for lunch. Suppose we also, coffee's not going to cut it though, is it? I don't drink coffee, but it smells good. Okay, suppose we also want the R's to be 10,000 ohms. What's that mean? Have to climb another mountain, don't we? We have to scale again. This now says that we have a k sub m, and we can find that now because we know what the new r's need to be, and they were all the same before. which allows us to just say, oh, all the R's, change them to 10K. R old was just 1. R new is 10, and now then we have a value of K sub M of 10,000. We can now find parameters or resistors and capacitors that will implement a 200 hertz low pass third order Butterworth filter by using these new values of R's and C's in that previous circuit diagram. By relating or making R bar the 10K, the bars now are the new, since I already have 1s and 2s floating around. The bars are my new parameters. And I started with an R, so now the R bar value is 10K. The R sub 1 bar is 10K, or that's K sub M times R1. That's all I'm doing. And the R sub 2 bar is also 10K, because they all started out being 1. My C's are a little bit different, because now those are, let's say, C1 over both of those scaling quantities, K sub F over K sub M. C sub 1 actually was 2, and if you plug in all of those numbers, you end up with 159.2 nanofarads for the modified or the scaled C sub 1 parameter, which we're now calling C1 bar, meaning that would be located right there. That's now our C1 bar. It would now be 160 nanofarads instead of 2. So we might be able to find something in that range a little easier than putting 2 football fields on our small circuit board, 2 farad capacitor. We have supercapacitors now, so that's not quite as bad as what I just said. But now we have C sub 2 bar. That's this 1/2 over these 2 parameters, scaling parameters. And that now becomes 1/4 of 160, or about 40. This is now 39.8 nanofarads. And finally, we had one more capacitor in the first order, or the first order stage on the right, and that had a value of 1. We divide 1 by all of those, and we end up with 7.96 times 10 to the minus 8 farads, or if we're going to keep units of nanofarads, we're up to about 80 nanofarads. So we have a 40, an 80, and a 160 nanofarad capacitor. And that really completes our design. How fast in the high frequency range will this filter roll off? What's the slope at high frequencies? What do you need to know to answer that question? This is a final exam question. You just need to know the order, don't you? It's third order, and each one of those contributes 20 dB per decade down. So it's minus 60 dB per decade is the slope, or the roll-off rate into the high frequencies. What's the cutoff frequency? In radians per second, it's 400 pi. In hertz, it's, isn't it 200? Is that what we wanted? 200 hertz. And we know the magnitude of that transfer function at that cutoff frequency is 0.707, or 1 over the square root of 2. What's the phase of this filter at high frequencies? We do not have any finite zeros, do we? So the numerator is not influencing our phase. We'll just assume that the sign of this is 1. It could have been a negative, but let's just assume that we're worried about nothing in the numerator. Then what's the phase at high frequencies? If I had asked you to sketch the Bode plot for this, could you do it? That's basically what I'm asking with some of these questions. What are some ways of checking your result? Where's the phase begin? At low frequencies, what's your phase? 0 degrees, right? Because we had nothing in the numerator, no s in the numerator, and our s's were all in the denominator. But if we let those be small, the only thing remaining was a 1 down there as a constant. So we have 0 degrees minus 0 degrees. It's 0 degrees. And then each of those 3 poles contributes minus 90. And so we end up at high frequencies with a phase of minus 270 degrees. Is that okay? Enough for filters. Let's now look at